of these things that I'll be talking about have already been shown in a few slides. But what I'm going to do is give an overview of what we're doing with Kepler, both what we've done in the past year or two, what we're currently have in the pipeline, and what we're hoping to do in the next few years. There's obviously a few of us working with here. Armin, who's also here at the meeting, and a few others in Maryland, and Gemini, and Alfredo, who a lot of us know, and Peter G. So we all have kind of different aspects of what we're working on, and we'll kind of summarize that. So firstly, what Kepler is. So for those of you who don't do planets, it's been spending a lot of time looking for planets, which we all know is kind of worthless. So we can figure out a better way to use that is finding supernova. So the benefit of Kepler is it has a large field of view. We've talked about field of views now, and it has over 100 square degrees. It has a high cadence, as it's been shown, so it observes the same period every 30 minutes. So whatever object falls in that area, you get a 30-minute light curve. It also has pretty precise photometry. So again, to find the planets, they need millimagnetometry. So that means you get supernova light curves or AGN light curves with millimagnetometry. The one downfall of Kepler in all this is the data download process. Because it's at a far orbit in L2, it can't download every single pixel. So you have to choose ahead of time. You have to predict where the supernova is going to be. So you actually have to kind of have some, put that astrology into what we're doing and predicting where things could possibly be. And if you don't, and the supernova occurs, you don't download it. There's also a delay in the data downloading, which means that even if you get a supernova, you have to wait months for that data to come to you to look at it. So you really need concurrent ground-based imaging in all of these things. And most people are aware that Kepler broke. So the new mission, which is called K2, uses two of the gyroscopes and the solar wind to act as a third pointing. So it uses two gyroscopes and points in a direction so that the solar wind blows on it, using it as this third steerable axis. What this means, however, though, is it operates and changes fields every 85 days. So instead of staying at the same patch of sky, you have a different field for 85 days. There is a benefit to that, though. It means that you get a variety of fields falling along the ecliptic, which means instead of just the original Kepler mission, which can only be done from the northern hemisphere, you can do it both from the north and the south. So with these alternating fields, you kind of get one that points towards the galaxy, one that points away from the galaxy. And when Kepler is pointing away from the galaxy, that's when we're focused on monitoring the extra-galactic stuff. So you can see a summation of all the fields that we've done, and we're usually doing anywhere between 2,000 and 5,000 galaxies on these 85-day cycles, which is quite a lot of galaxies to get objects at. And I'll talk about in a little bit about the ones that we're planning to do in the next few years. But from the original Kepler mission, so this is an example light curve. The black is the individual data points. So those are the 30-minute light curves you get from Kepler. Even bend, you can bend data at this rate and get it into 12-hour bins. Overplotted in the blue is a 2011 FV. So you can see how sensitive, both in terms of early times and the cadence that you're getting of these objects. So for the original Kepler mission, we had 6, 3 1As, which have been talked about, a couple 2Ps, and a 2N or a 1A CSM. With K2, we're at 18 objects now, so these are a variety of the light curves that we had. We have 10 1As and even a 99 AA-like object. We have a few core collapse, and we have a weirdo, which I'll show in a second, that Armin Ress is winding up. More importantly, in addition to all these, we have just light curves of galaxies. We have about 23,000 of these high cadence light curves of galaxies. And we're planning on releasing these to MAST in due time, so that if you want to do a large study of small transients, faint transients, you could look for these things. Additionally, with every field that we're monitoring in K2, we do very large mass, so we do very large coverage of the extremely nearby galaxies. So anything that actually has a catalog name, the Messier galaxies, NGC galaxies, we have a very large mass to look for, Novi, CVs, other things like that. We're actually getting quite a good redshift range, almost up to 0.2, which gives us quite a lot of depth in terms of where we're looking at. So with some of the 1As that we've done, and Tony just showed some of these, that with the cadence that we're getting and the sensitivity, we can put strong constraints in some of these shock interaction models for 1As. And then at the very least in 2 of the 1As from Rob's paper last year, we can really constrain that the radius of the progenitor, so the radius of the donor star in the 1A had to be less than the solar radii. So we all know that we can never say that it is a white dwarf because they're very elusive and it's kind of like a unicorn. They might not actually exist. But we can at least say that it has to be from less than the solar radii, which doesn't give us a lot of progenitor scenarios that can create this situation. Additionally, with the probing of the rise, you get very accurate rise times, and there was always this generally feeling that you get a nice approximation of t squared and approximating how these things are exploding. But with each light curve and each explosion, we're able to see that the early power law, the early explosion model, is different for every 1A. So you get some that are about 2.1, 2.2, and some that are 2.5 and 2.6. So some are actually exploding faster than others. And this is exactly what people we've seen in 2003 or 2013 DT, 2014 Che, 2011 FV. There's now a number of these 1As that show that the early explosion is different in all of them. And more importantly, that if we're getting different progenitor scenarios, if we do have the single degenerate companions like what was found in 2012 CG or IPTF11KXY, but then we also have some very small progenitor systems all rising differently. We really have to start thinking about that, what it means with cosmological light curves. Now, speaking of that, this is probably the first and potentially the only cosmology paper from Kepler. So we have fairly faint declining 1As in the first sample, which isn't surprising that we ended up targeting elliptical hosts. Alfredo Zenteno right now and Ashley Miller are doing a full analysis, including the 1As that we have from K2 with these, looking at some of the models that Tony nicely summarized, and trying to see statistically what are the progenitors that could be coming that we can detect or not detect in the 1A sample. So hopefully that should come out in the next few months here. Also, what was briefly shown is both of these in different talks, surprisingly. These are 2 of the 2Ps that we had in the original Kepler mission. And on the right, in Peter's paper a few months ago, we see a clear, what as Tony defined as the shock breakup. So this is the shock wave reaching the star within the first minutes of explosion. It was not seen, and that was seen in a larger red giant, almost 500 solar radii. In the smaller progenitor, we don't see anything, and this is what Francisco was talking about, where we believe that there's a lot of extra circumstellar material. So the green line is the best fit stellar radius model, and there's a lot of extra material for days around the early times of explosion, which is probably the result of extra material being around this star. And now that also it's been seen in other surveys, this isn't a byproduct of Kepler, it's a byproduct of actually being able to measure these things early. There is something going on, and there is something to learn about progenitors. What it is, I don't know, but there's something to learn. Now, one of the other things that we've just been looking at and discovering is that in one of our 2Ps, on the top here, it had this weird secondary maximum. So instead of just declining into the normal plateau phase, it actually rose, had a maximum, and then declined again. And somewhat slightly similar to 1999 EM that Mario wrote a great paper on, with a slight, there was only one data point, but in the R, when you look at it, it has this very strong maximum. And we've all believed that it's because of hydrogen recombination, that there's a plateau phase, but now we can actually see it live. So if you look at the spectra around this time, so if you sample around maximum and getting down to this phase, what you see is as you reach maximum here, hydrogen increases, you decrease as you go off the maximum light, and then as you reach the secondary bump, you get a huge amount of emission coming from hydrogen. So what you're actually seeing is the exact beginning of hydrogen recombination taking place in this explosion. So now you can clearly say that the type 2b plateau is from recombination because, well, we're seeing it live in these things for now. We've also been able to see dust interaction at very long times. So this is an object that has some sort of circumstellar material in one of our light curves, and these individual bumps, so keep in mind this is on a time scale of about 2.5 years. that all of these individual bumps that are lasting 10 to 20 days are actually material from the supernova interacting around it. So we can actually see this ejected material having interaction. One of the new things, and this is the weirdo that Armin is writing up, is we think maybe it could be a 0.1A. So this rise time is 2.2 days. It reaches a peak magnitude of around minus 18.7 and declines in just about 12 days. It's also very blue right around maximum. We didn't get a spectrum of it because we thought it was an asteroid because we had one detection of it and then it was faded because it went so fast. But it is a very fast rise. It's not quite faint, but it is blue. And this has been shown, and if you plot where this object lies on the figure that Metzi made previously, 2015K is kind of just to the left here in this broad 0.1A predicted region. It's a little bit faster than O2 BJ rather. But what is, I think, quite interesting is this slight secondary bump, which obviously we see in 1As, but we kind of see in this object too. So looking forward, we are currently monitoring this campaign C10, and as soon as Armin can get connected to send the ATEL out, we have 2 candidates that are going on right now in Kepler that was found through DECCAM imaging. Excuse me. And we're doing a few more fields. Now the problem with Kepler right now is that it's always looking towards the ecliptic and towards the sun, which means the fields are only up for about an hour or 2 at the beginning of the night and then set towards the end of the field. C17, which will be this exact same field in a year and a half time, will be revisited, but instead of looking away from the sun and the earth, we're actually looking towards the sun and the earth, which means the whole field will be up for the entire night. And because of that, it will allow full ground-based coverage and monitoring the whole time the field is up, and also be able to allow us to get full color, full spectral information while we get the Kepler cadence of this. And so we should be doing in this field between 10 and 30,000 galaxies, depending on how many we can calculate, we can download. Now just ending, because I know, Mark said he started on this, so you can do AGN. So we didn't forget supernova, so I know Mark likes AGN, and we can do, low-level AGN down to 1 or 2%. We're even starting to do quasars, so you can actually see quasar variability on less than the scale of about 1% too. So we're getting lots of great things with Kepler. I think we're shown both here and in the previous 2 talks that not only early time observations, but frequent observations, allowing us to probe a lot of the physics that's either been predicted or we haven't thought of looking for. And with continuing these things and also different wavelengths, we can actually start to figure out some of this physics that Nick talked about, putting the astrophysics into supernova again. And so we have a lot more campaigns that we're doing. As I said, we'll also be releasing most of the light curves for even the non-transient objects via mask. And we will be having a broader focused meeting for anyone interested roughly in February when we set the dates at NASA Ames for both planning for these future fields and the science that we've done with the objects we've already monitored. So I'll end there. Thanks.
Thanks. Question? Nick, closer.
This is a stupid question. I don't know what a 0.18 supernova is.
Okay. So Nick doesn't know something. Well, at least you know the photometry right now. So 0.1A is a predicted model, and Ken Shin, who's sitting in the back of the room trying to hide, might be able to talk a little bit more about it. So we believe these are 10% the yield, whatever the plot is, 10% the yield of a 1A explosion. It could be possibly from a helium star, correct, Ken?
Yes.
Yes.
The helium powder.
Yeah, there you go, yeah.
So you've created morphological classification based on theory, right? It's not an observation, it's a theory.
Well, we have an observation now.
Yeah, but it was originally classified as a theory, you found an observation.
Yeah, so it's not a theory.
But okay.
Well, no, but I think it's great, right? We're not creating a theory to match an observation. We've actually an observation to match a theory.
So far, yes. Okay.
Yeah, when we get 2, we have a class.
There are other candidates.
Yeah, there are others. There's an O2BJ. There's a few other potential ones that are like this too.
Yeah.
Yeah.
So going back to observational reclassifications, you showed 3 of the 1As in the paper, which was very, very interesting. So I'm wondering, with the other 7, is there any interaction that you see at the beginning?
So these are 3 from the first 1As. We have an additional 10. So we have a total of 13 now 1As. So
Okay.
3 with the original. This is exactly what Alfredo is writing up, is looking for the interaction, both using Dan Kaysen's models and some of the other newer models, and some in population synthesis models. Yes.
And any preliminary things you can tell us? Any interaction that you guys see?
No, I'm not saying.
What about open science here?
What about open beer to get me to tell you that science?
The second sentence.
The cycle 17 stuff is public, right? It's not just like you guys are doing this, it's Kepler.
So for everything here, all of the data is automatically public. So you can actually access, as soon as the data is downloaded from the telescope, to go and look and analyze the galaxies yourselves. However, Kepler born is a systematic nightmare. And the stuff how they find planets, I think it's just made up. In order to get the supernova stuff requires a lot of work to get it.
No, but what I mean is that they're doing a microlensing campaign like this.
Yep.
If they turn the spacecraft around, and it's a big hit on their operations and the way they do
Yes,
everything.
that's why
The
we're looking.
idea is to make it so that the community can get a big impact out of something. Because
Exactly.
it's like, we'll turn Kepler over to supernova science effectively for a cycle.
Yep.
So the point is the community needs to get behind it and getting light curves and get involved. It's not just like your team gets a cycle of Kepler.
Right, exactly. And this is the whole point of having a planning meeting in February, is it will be available for anyone who cares about anything beyond the galaxy.
Okay. Thanks again. And we move to the next speaker.